The internal random kinetic and potential energy is the internal energy, and that is what is transferred between two objects when their temperatures are different. Okay? Heat can be used to do work. Okay? And now in the next two chapters, we'll learn that if you had 100 joules of heat, you can't convert all of that to work. Okay? So thermodynamics really was born out of that, when we started using steam engines and stuff like that. Do you guys know of examples of heat engines that we use in our life? I'm sorry? Cars. We use a lot of them. Thermal power plants, nuclear power plants, all of them are converting heat to energy, to other forms of energy. And as you saw, it is very inefficient. The best in practice what we've been able to do is, so it's a coal power plant, and for 100 joules of heat, we've been able to convert 40 joules to electricity. That's the best we can do. In a nuclear power plant, we can convert 100 joules of heat to 35 joules of electricity. In your car, 100 joules of heat is converted to 20 joules of motion. All right, so what we're interested in, how to convert heat to do work. Okay? So any form of energy can be converted to any other form of energies, but some conversions are more efficient than others. So mechanical energy to heat, you can convert 100% of that. Heat to mechanical energy, that's about 30% efficient. What happens to the other 70% of heat? What happens to the other rest of energy? Stays as heat. Okay, so if you put in 100 joules of heat, 30%, 20 joules got converted to work, and 80 joules remains as heat. Okay. All right. So in a car, heat is obtained from burning gasoline and converted to mechanical energy. And what you don't convert to mechanical energy goes out to your tailpipe. Okay. All right, so now let's define some terms. What are thermodynamic systems? Thermodynamic systems are systems that contain a large number of particles. And what do we mean by large number of particles?
Like on the scale of Avogadro's number?
That's right, okay. Can you give me an example of a thermodynamic system?
This room?
The gas in this room, you're a thermodynamic system. That table is a thermodynamic system. The walls are thermodynamic systems, okay? So you're surrounded by thermodynamic systems all around. All right, so this is called the system. That's the boundary, okay, and this is the surroundings. Okay. It's lagging.
It's doing that thing where it repeats everything you've done so far really quick.
Is it back on? No. All right, I guess I'll. Okay, I guess we get a 3-minute break.
It's review time.
What's that? Yeah?
I said it's review time.
All right, yeah, it's review time.
Quickest.
Hey, at least it's not
It's going pretty fast.
Looks like you've selected screen and highlighted it.
What?
Well, it's blue. Oh, I think. It's like my copy.
It seems like it. Is this happening on my iPad?
Oh, you can't see it.
No, no.
I think
Is it happen? Well, so it's happening in the projector memory. I mean, where is it happening technically? Anyway. All right, so looks like we're on. Okay, so there's the system, there's the boundary, there's the surrounding. So to use this room as an example, the system is everything inside the room, the boundary would be the walls, and the rest of the universe is the surroundings. Okay, so here's the car, a piston in your car. There's the boundary, there's the system, and there's the surroundings. Okay. We have open and closed systems. Open systems will exchange material particles with the surrounding. Closed systems, the number of particles is constant. Okay. So you will learn. We won't deal with it, but you will learn that there's something you can define a chemical potential, and if there is a difference in chemical potential with the surroundings, then you can exchange particles. Okay. Reversible and irreversible processes. Okay. So let's say you have a system. So this is a reversible process. We are showing you a reversible process. You have a system, you do something to the system, and then you bring back the system to its original shape, to its original state. And it's a reversible process. If you can bring back the system and the rest of the universe to its original shape, to its original state, then it is a reversible process. Okay, so you have to bring everything back to its original state. Okay, so for instance, what I can do is, let's say I have a cup of hot water. I place it in the room. What will happen? I'm sorry? Yeah, heat will flow out of here. Heat will flow out of here, go to the room, and the temperature will even out. What I can do is I can use a heat pump, remove the heat from the room, and put it back in here and warm up the cup. Except that so the cup will come back to its original shape, except that the use of heat pump warms up the universe. So in all processes that you can think of, you can never bring back the system and the universe back to its original state. All natural processes are known to be irreversible. Okay? So this process, which was natural, heat flowing from the hot cup to the room, that was a natural process, and that is irreversible. Okay? Well, then why the heck do we define reversible processes? So this is an ideal process. It's a frictionless process and stuff like that. This kind of stuff is useful in calculating upper limits for things. So when we want to calculate what is the best you can do with a heat engine and stuff like that, these processes will be useful to establish upper limits. Okay? So there's no such thing as reversible process in nature. Okay? But it's a theoretical concept that's useful. Okay, so again, all natural. So what is a reversible process? If a process happens, and if you can bring back the system and the universe back to its initial state, that process is a reversible process. Okay? But there's no real life example of it. All right, so in our lives, we use gases to do a lot of work. Okay. Can you give me an example where you use gas to do your work?
Drinking from a straw.
What's that?
Drinking from a straw.
Yeah.
And also pistons.
In your car, you burn an air-gasoline mixture, you get the piston moving and get the car moving. In a thermal power plant, you burn coal. From the heat released, you boil water, and the steam is turning a piece of wire between magnets to produce electricity. Have I shown you the generator? So you tie your dog to the wire and then make him run. In a windmill, the wind is turning the blades, which is turning that wire.
I was gonna say, these have like emergency flashlights and radios and things that you
Right,
bring.
it's exactly the same thing. So in a windmill, winds are turning the blades, which is turning that wire. That's your ultimate goal. In a dam, the flowing water is turning that wire. In a thermal power plant, you burn coal. What do you do with that? From the heat produced, you boil water. The steam is turning that wire. In a nuclear power plant, if you want to see one, we can see one at UF on on the 27th. In a nuclear power plant, you're splitting atoms. Heat is generated. What do you do with the heat? Boil water. Why do you boil water? Huh? What do you do with steam? Turn that wire. Your goal in life is to turn that wire. Okay? So you figure out this little device, there's trillions of dollars invested in this thing to turn that wire. Okay. And what is this contraption doing? What is it doing ultimately? There you go, my friend. Okay. So that's what, okay. All right. Anyway, we use gases quite a bit. Okay. So if you put heat, add heat to the gas, it can lift up the piston, which is used. That's how you do work using this gas. Okay. All right. Now, before we go there, so whenever you're working with gas, any process, it's very convenient to depict the process in a PV diagram, in a pressure versus volume diagram. Okay? So whenever you're working with gases, so if you see a PV diagram, that means the system you're working with, the thermodynamic system you're working with is a gas. Okay? If you're working with a liquid or a solid, then you don't draw PV diagrams. Why don't you draw PV diagrams for liquid and gases?
The volume doesn't change.
The volume doesn't change a whole lot. The pressure doesn't change a whole lot. Okay, so all it'll end up happening is you just plot a point. Okay, so as soon as you see a PV diagram, what you know is in your head, you know that you're working with a. This is very interesting. Oh, wow. All these apps hang up after a while. You got to constantly talk to them. All right, so here's a gas. The gas is at 26 atmosphere. It's at 300 degree Kelvin. Okay, what I'll do is I'll keep the pressure constant. Okay. So I'm going to heat this gas and watch the pressure will be constant and watch what will happen to the temperature and volume. Okay, so I'm going to heat the gas. So you see the volume increased and the temperature increased. Okay. All right, what I'm going to do is I'm just going to plot the state of this gas on a pressure versus volume graph.
What they taught.
So here's the pressure and volume. Okay, so as long as I'm dealing with pressure, volume, and RT, remember the number of moles of gas were constant, R is constant. So if I know the pressure and volume, I can calculate the temperature. Okay, so this was the initial state of the gas. This was the initial pressure and volume. I added heat to the gas.
How long it takes a beginner
happened
like my
when I
dad
added
to
heat?
go from beer belly to get ripped again with Tai Chi.
Volume increased, the pressure was
What you're
constant.
looking at is a very
So that
simple
process, what I
alternating
did
current or
was
AC
like that.
generator, a device that converts mechanical energy.
You see, that's so beautifully, so succinctly represented by this diagram, on this diagram. So you can represent various processes on this PV diagram as long as you're working with the gas. Okay? And this is a very useful device. Okay, let me show you another process. Okay, so let's keep volume constant. Okay, and now I'm going to add heat. What will happen? The pressure increased and the temperature increased. Okay. So on this PV diagram, how do I show this process? Okay. So this process will be. So here was the initial state, and this was a constant volume process. Okay. So on the PV diagram, you can show all these various processes very, very nicely. Okay, and that's a useful thing to do. All right. So here is the pressure, volume. Okay. So what you're doing is taking the gas from this initial state to that final state. Okay. This initial state to that final state. This initial state to that final state. Okay. So for an ideal gas, PV equal to nRT, if the temperature is constant, okay, so P is nRT over V. Okay, so you can express pressure as a function of temperature and volume. Okay, so let's say if you keep the temperature constant, this would be a hyperbola. Okay, anyway, so let's say you took the gas from here to there along that path. You can take the gas from here to there along this path. Along this path, there's an infinite number of ways of going from that initial point to the final point. When the volume changes by a small amount, this is the amount of work done by the gas. And if you integrate that, then you get the total work done by the gas in going from this initial point to that final point. And if P is a function of V, what does this integral give you? It gives you the area under that curve. All right, so you can take a gas from an initial to a final point. The work done by the gas is the area under this curve. Why are we learning this? Well, because we use a lot of gas to do our work. Okay? And so now we've shown you how to calculate the work done by the gas. So if the gas goes like that, okay. Now what do you see in these graphs? To go from the initial point to this final point, how many ways are there? How many paths are there to go from that initial point to that final point? I'm sorry? An infinitely many number of paths. The amount of work done is path dependent. It's different for different paths. Okay? All right, so the work done depends on the path. A system can be taken from an initial state to final state in an infinite number of ways. The work and heat exchanged are path dependent. Okay? So the amount of heat added to the system and the work done by the gas, they're path dependent. Okay? Now here's the deal. So when the gas is in this state, each point is a state. That's the initial energy of the gas. That's the final energy of the gas. So let me ask you this. If I come to that final state along this path, does the final energy of the gas change? The energy of the gas is a state function. So it doesn't matter how you got there. The energy of the system is the same. Okay, so the change in internal energy of the system is path independent. Okay? Internal energy is a state function. So now we're ready to give you the first law of thermodynamics. So the change in internal energy is the heat absorbed by the system minus the work done by the system. Okay, so this is path dependent, this is path dependent, but their difference is path independent. Okay? So the change in internal energy of the system is the heat added minus the work done by the system. Now we've illustrated this for gases. What is this valid for? What is this true for? It's true for all thermodynamic systems. Okay? The change in internal energy of the system is equal to heat added to the system minus the work done by the system. Okay, so if I add this heat to a cup of water, how much work does a cup of water do? It does nothing. Okay, so this will be zero. All the heat added will go into changing the internal energy of the water. Okay, so here's the first law of thermodynamics. All it tells is where did the energy go. You added heat to a system. If the system did work, the heat added minus the work done goes into increasing the internal energy of the system. Okay? A good way to think of this is in finance. This is your bank balance. This is your earnings. This is your expenditure. If you earn $100 and spend $40, your bank balance increased by $60. Okay? All right, so again, it's just telling you it's just a conservation of energy principle. Okay? Did you guys understand that? Okay. So now here's, so in different books, they have different sign conventions. Okay. Even in physics books, sometimes you have different sign conventions. Engineering books tend to have different sign conventions than physicists. So just be aware of this. So let me tell you the sign convention. We are going to stick with this in this course. Okay, so this is the system. If the system absorbs heat, Q is positive. If the system does work, W is positive. If the internal energy of the system rises, delta E is positive. Okay? And that is universal. If the internal energy of the system rises, that's positive. Okay. So if you do work on the system, for instance, you can take a gas and compress it, then the work done by the system is negative. Okay? So you will always look at things from the perspective of the system. If the system does work, work done is positive. If you do work on the system, the work done by the system is negative. Okay, so that's the convention. W is positive when the system does work. Okay. Okay, so again, the first law of thermodynamics is very simple. Okay. This is internal energy, this is heat, this is the work. Okay. So if you add heat to the system, this is positive. If you remove heat from the system, that's negative. If the system does work, that's positive. If you do work on the system, that's negative. If the internal energy increases, that's positive. And if the internal energy decreases, this is negative. Yeah. All right, any questions before we go on? All right, so here's a PV diagram. What does that tell you? What is your system? Your system is a gas. Your thermodynamic system is a gas. Okay. If it was a solid or a liquid, you wouldn't be using PV diagrams to describe various processes. Okay. So our system is a gas. We're going to use a PV diagram to describe various processes. Okay. And these are some processes that you have to know about. Okay. Isovolumetric process. Iso means constant. So your system is going through a process where the volume is constant. Okay? So volume is constant. So on a PV diagram, what kind of process will that be? That will be vertical lines. Okay? Because volume is constant. You can increase the pressure. So how would this happen? How would this process happen? For instance, this was the initial state, and that is the final state. How would you do that process? What would you do to the gas to go along that path? You would have to heat up the gas to go along that process. This is, you're removing heat from the gas, okay, at constant volume. So I draw a process, and you should be able to think about the physical thing that's going on, okay? So an isovolumetric process is where the volume is constant. So here is an isovolumetric process. Okay. Isobaric process. Pressure is constant. Here is an isobaric process. Okay. And I showed you how to do an isobaric process. Okay. So in an isobaric process, okay, again, you can assume that we're dealing with ideal gases. So as you add heat and increase the temperature, you're letting the volume increase as well, such that the ratio remains constant. So that's an isobaric process. An isothermal process, you're letting the temperature is constant. Okay, so if the temperature is constant, this is constant, and the pressure, as volume increases, the pressure decreases along a hyperbola. Okay, so when you take the gas along an isotherm, this is how the process looks like. Yep. All right, this is at a lower temperature, these are at a higher temperature. As this constant gets bigger, the hyperbola shifts to the right. Okay, so this is a higher temperature than this, and so on. An adiabatic process. In an adiabatic process, Q is 0. Okay, what does Q equal to 0 means? What does Q equal to 0 means? Yeah. Q equal to 0 means you're not adding heat to the system or removing heat from the system. Okay? So what that means is if the system does any work, then if you're not earning anything and you spend money, if you spend $100, then your bank balance decreases by $100. Okay? So if you do work, then that energy is coming from your internal energy. Okay? So that's an adiabatic process. Okay, so you have to be aware of these 4 processes. All right? Now we'll say something about each of the process. Okay? So a cyclic process, as the name suggests, a cyclic process, let's say this was the initial state of your system, you take it through a cycle, okay, and that's a cyclic process. Why do we talk about cyclic processes? In all your heat engines, you take your system through a cyclic process. You put in gas, so it's sort of a cyclic process. You put gas air fuel mixture, you compress the gas air fuel mixture, light it up, and then get work out of it. And then you exhaust, but then again you recharge it with air gas mixture. You're going through the cycle. Okay? So all your systems go through cyclic processes. Okay? So in this, you're not recharging and stuff like that. So if you take a closed system and go through a cyclic process, the total internal energy change, because you've come back to the same spot, is internal energy change is 0. So any heat added, that's converted to work. Okay? The net work done per cycle in a gas is equal to the area enclosed. So, and the work done by the gas is this area. Isothermal process. In an isothermal process, internal energy doesn't change. So the internal energy is constant along an isotherm. Okay? E is constant along this process. And the work done is equal to the heat added. Yep. Whatever heat you added is the work done. In an adiabatic process, Q is 0. The work done, if you do positive work, then your internal energy decreases. In an isothermal expansion, so here is an isothermal expansion, the work done is the area under this curve, and now we can show you what this area is. Okay, so for an ideal gas, P is nRT over V. So here's P as a function of V. In an isothermal process, T is constant, so this guy is constant. This is constant over V. So this is equal to nRT dV by V. Okay, so dx by x. The log integral of that is log V. Okay, and then you apply the limits. So the work done is nRT natural log of V final over V initial. Okay. So this area is equal to that. So that was easy to calculate. All right. So what we are doing here is, for the various processes, we are saying something about each of these terms. So what are the processes that we've learned? Isovolumetric. What is an isovolumetric process? Volume is constant. For an isovolumetric process, this is 0. What is an isobaric process? Pressure is constant. So for an isobaric process, work done is just the constant pressure times the change in volume. It's this area. Okay. So we are saying something about that. Okay. An isothermal process, I showed you how to calculate the work done, and we'll tell you something about the adiabatic process. So in an isobaric process, that's the work done. In an isovolumetric process, this is an isovolumetric process, the area under that curve is 0, the work done is 0. Okay. All right, now is a good time to stop. Okay.